Hi folks, how y'all doing? We are covering section 3.5 today, which is on subspaces. Let's go ahead and dig in. So our definition is that a subspace of Rn is just any subset of Rn which happens to be the span of a set of vectors. And so I want to sort of emphasize this point. All spans are subspaces. That is, any set that is just an entire set of linear combinations of a set of vectors, that is a subspace. So let's look at some examples. Let's use the definition then to show that this set of vectors in which x is 2w plus 3y and z is 4w minus y is a subspace of R4, excuse me. So we have a vector w, x, y, z. X is 2w plus 3y. And z is 4w minus y. So I'm replacing x and z with this statement. Well, I can rewrite this as w times the vector 1, 2, 0, 4 plus y times the vector 0, 3, 1, negative 1. But this is the form of a linear combination. W can be any weight attached to this vector, y can be any weight attached to this vector. And so this set is the span of the vectors 1, 2, 0, 4 and 0, 3, 1, negative 1, and all spans are subspaces. And so by the definition, this set is a subspace of R4. Again, I can't draw this because we're in 4 dimensions, but we would have 4 axes, a w-axis, an x-axis, a y-axis, and a z-axis. But we have these 2 vectors, 1, 2, 0, 4, and this other vector 0, 3, 1, negative 1. I'm not drawing a scale or anything. And the linear combinations of those 2 vectors forms the plane that contains those 2 vectors. So it's not all of R4. It's just a subspace of R4. It's just part of R4 that they span. So I want to be careful about this. The span does not equal R4. But it's just a subspace for R4. All right. Let's move on. We have this theorem, and we've seen these definitions before. S is a subspace of Rn if S is closed under addition and if S is closed under scalar multiplication. That is, whenever U and V are in S, then their sum is also in S. Whenever U is in S, all scalar multiples of U are in S. And so we have this theorem. This actually closes up a loop. That is, if I have a set that is a subspace or a span, then it's closed under addition and closed under multiplication. What this theorem says is that if it's closed under addition and scalar multiplication, then it's guaranteed to be a subspace. In other words, it's not possible to have any set of vectors that's closed but isn't a subspace for somehow. That is, that if you have a subspace, then it's closed under addition and multiplication, And if you have a set that's closed under scalar multiplication and addition, then there is a way to show that it's a subspace. Okay? All right, so let's look at this example. We're going to look at all of the vectors in which y is equal to 2x. So number one says to give an example of a vector that's in S and a vector that's not in S. So to be in S, the only thing that has to be true is that y has to be 2x. So we could have, for example, 3, 6, and negative 2. Y is equal to 2x. And so this vector is in S. So if I want a vector that's not in S, I just have to make sure that y doesn't equal 2x. So 5, 7, and 1, y doesn't equal 2x. And so this vector is not in S. All right. How many vectors are in S? Well, there's an infinite number of vectors in which y is equal to 2x. There's an infinite number of vectors in this set. And so this is a set that's too large to write out, but we can still talk about the set. We're continuing with the example on the next page. Is S closed under addition? So in other words, if I have two sets, say x1, and then y has to be 2 times x, and then z1, and then another vector x2, and y has to be 2 times x, so y is 2x2, and I add them together, I get x1 plus x2. When I add these together, I'll factor out the 2, I get 2 times x1 plus x2, and then z1 plus z2. And once again, y is equal to 2 times x. And so if this vector is in S and this vector is in S, then their sum is in S also. And so, yes, this is closed under addition. Is S closed under scalar multiplication? So again, I have some vector x. The y-coordinate is 2 times x. And then we have a z-coordinate. And I multiply it by some constant k, well, then I get kx, and then I get 2 times kx, and I get z, and the y-coordinate is still 2 times the x-coordinate, and so if I scale this vector, it still obeys the rule that y equals 2x, and so yes, it's closed under scalar multiplication also. And so by the theorem that we just said, if the set is closed under addition and scalar multiplication, then yes, it's a subspace, which means we can write it as a span. And the way to do that, since y is equal to 2x, is to write this as x times 1, 2, 0, and then we have a z also, z times 0, 0, 1. And this is a span of the vectors 1, 2, 0 and 0, 0, 1. Okay. So it is a subspace. In fact, it's a span. But even if we didn't know that it was a span, we could tell because it was closed under addition and closed under multiplication that it had to be a subspace. Let's move on. How about these sets of vectors? Are these sets of vectors subspaces? The set of vectors x, y in R squared where x is greater than or equal to 0. So that is this set of vectors here. All of the vectors in which x is greater than 0. So to be a subspace, the things that we have to check is it closed under addition. If I take two vectors in which x is greater than 0 and I add them together, will the total still be greater than or equal to 0? And the answer is yes. But is it closed under scalar multiplication? And the answer to that is no, because I could have the vector 3, 7, but my weight could be -2. The requirement is that x has to be 0. It doesn't tell you anything about the weight, and then when we weight them together, we get -6, -14, and that's no longer in the set. And the set is not closed under multiplication. And so this is not a subspace. So what about the set of points that's on the line y equals x? So is it closed under addition? If I take 2 points that's on the line y equals x, that just means that the x coordinate and the y coordinate are the same. So it might be like x1, x1 plus x2, x2. If I add them together, will the x and y coordinates still be the same? Of course. I just get x1 plus x2 for x, and I also get x1 plus x2 for y, and so that's still on the line y equals x. And so yes, it's closed under addition. Is it closed under scalar multiplication? So if I have a vector where the y coordinate and the x coordinate are the same, and I scale it by any weight, will the x coordinate, y coordinate still be the same? And the answer to that is yes, of course, that the x and the y coordinates still match. And so even if we scale the vector. And so it's closed under addition, it's closed under multiplication. That means this is a subspace. All right. Let's keep going. All right. Let's let A be an m by n matrix, so this matrix doesn't have to be square. Then we have 3 subspaces that are associated with the matrix A. They're called the column space, the row space, and the null space. The column space, which we just abbreviate as COL of A, is the span of the column vectors of A. I just take the matrix, divide up the columns into individual vectors, take their span, and that gives me a space. That's usually pretty easy to work with, but we will do some examples in a moment. When A is an m by n matrix, that means it has m rows. That means every vector that's in the set will have m entries in that vector, so it's going to be a subspace of Rm. The row space is the span of the column vectors of the transpose. And we take the transpose, which switches the rows and the columns, and then instead of getting a subspace of Rm, we get a subspace of Rn instead, because the columns and the rows have switched places. And the third type, which is called the null space, is the solution set to the homogeneous equation Ax equals 0. It turns out that set is always a subspace. And it's a subspace of Rn, and we will take a look at that today as well. So we're going to see examples of all 3 of these types of subspaces in a moment. So we'll start with column space. Let A be a matrix and A1 through AN be the columns of A. If I take the span of those columns, I get a subspace that's called the column space of A. So as an example, if we're going to describe the column space of this matrix A, the column space of A is the span of the columns 3, 2, and 5, -1. That's it. Ta-da! It turns out in this special case that because 3, 2, and 5, -1 have a pivot in every row and every column. There's only 2 rows and 2 columns. We talked about this last time. That means that they form a basis for R2. And so in this case, we could just write this as R2, because the span of those vectors is the entirety of R2 and not just some subspace inside R2. Okay? Let's look at the column space of these 3 vectors. Well, the column space of these 3 vectors is the span of 0, 3, 1, 1, 2, -3, and 2, 4, -6. In this case, we do not have a pivot in every column, in every row. Because these 2 vectors are multiples of each other. The second vector, 2, 4, -6, is just 2 times 1, 2, -3. And so these 2 vectors point in the same direction. And so we're not going to have 3 pivots. We're only going to have 2 pivots. And so this is a subspace of R3 and not all of R3. This is a subspace of R3, but not all of R3. All right. Let's keep going. So what if we wanted to describe the column space of this matrix in simplest form? So in the last example, we said it was the span of these 3 vectors. But in simplest form, we are not going to need this 3rd vector. Let me show you what's going on here. I'm going to row reduce this quickly, or I'll try to row reduce this quickly. 0, 3, 1, 1, 2, -3, 2, 4, -6. I'm reading down. We're going to switch row 1 and row 3. And then take row 2 minus 3 times row 1. That gives us 1, -3, -6. 0, 2 minus -9 is 11. 4 minus, let's see, -18 is 22. 0, 1, 2. And then we'll take row 3 times 11 minus row 2. And we get 1, -3, 6, 0, 11, 22, 0, 0, 0. And we only have 2 leading entries in our echelon form. That tells us that this vector is necessary and this vector is necessary. But this vector is not necessary because any linear combination that includes this vector can just be rewritten as multiples of this vector. And so in simplest form, the column space of A is the span of just these 2 vectors, 0, 3, 1, 1, 1, 2, -3. the third vector is redundant and therefore not necessary. So identify the pivot positions. And use only those vectors. From the original set. I want to be careful, don't use these vectors. We're not using the vectors from the echelon form, we're using the vectors from the original set. All right, but that's the column space in simplest form. So we know how to answer questions about column space now. If the question is to describe the column space and they don't ask for the simplest form, we can just list all the vectors and put the word span in front of them. If we want simplest form, then we need to identify which columns have the pivot positions in them and just list those columns by themselves with the word span in front of it. Let's move on. So let's say we have a matrix and these are the columns of A. The columns of A transpose. Then the span of these columns is called the row space of A. So the only difference between column space and row space is that we transpose the matrix first. So let's describe the row space of this matrix in simplest form again. So we're going to transpose the matrix A. So the first column is now 0, 1, 2. The second column is 3, 2, 4. And the last column is now 1, negative 3, negative 6. And now none of these columns are multiples of each other. We have these rows that are multiples of each other, but not the columns. Is that going to change how the pivots work out? Well, we can find out. I'm going to put this 1 up in the top position. So 1, 2, negative 3, 0, 3, 1, 2, 4, negative 6. So I just switch these two rows. And now I'm going to do row 3 minus 2 times row 1. And 2 minus 2 is 0, and 4 minus 4 is 0, and negative 6 minus negative 6 is 0. In fact, we get to echelon form even faster because this row and this row are multiples of each other, so they cancel out quickly. And so we still have a column with no pivot position in it. And so in simplest form, the row space is the span of just the columns that have the pivot positions, but I have to go back to the original matrix to pull the numbers. 0, 3, 1, and 1, 2, negative 3. And this last column is not necessary. No. This isn't the matrix we're working with. This is the matrix we're working with. 0, 1, 2, and 3, 2, 4. Because it's a row space, we're working with the transposed matrix. So it's these two columns. I almost messed that up. Did mess it up, but caught myself. All right. Let's move on. So let's talk about the null space. The null space is the solution set to the homogeneous equation. So we know how to solve the homogeneous equation. We augment with zeros, we row reduce, we put the solution in parametric vector form. We did this on the first test. Let's see how this works out. So let's look at the null space for this matrix. So we're going to look at this system of equations here. All right. Well, we've put this in echelon form before, but let's do this one more time. I'm going to switch to 2 rows, 1 and 3 this time. 1, -3, -6, 0 goes on the top. And then we'll cancel that 3. Row 2 minus 3 times row 1. And that gives us 1, -3, -6, 0. 0, 11, 22, 0. 0, 1, 2, 0. And all right. Row 3 times 11 minus row 2, that cancels this out. So we're going to have a free variable. I'm going to go ahead and finish putting this into reduced echelon form so that we can analyze that free variable. So we'll take row 2 divided by 11. And finally, row 1 plus 3 times row 2. And that gives us 1, 0, 0, 0. 0, 1, 2, 0, 0, 0, 0, 0. And so we get x is equal to 0. Y plus 2z is equal to 0. And that's the same as saying that x is equal to 0, y is equal to -2 times t, and z is equal to t. And that's just saying that x, y, z, let me clear that out, is t times the vector 0, -2, 1. But this is the span of the vector 0, -2, 1. And that's the null space of A. Spans are subspaces. The null space is a span. It's the solution set that we get written as a span instead of written as a parametric vector form. That's our answer. All right. Let's keep going. Let's describe this null space. So let's see, 1, 1, 3, 0, 2, 1, 4, 0. We'll take row 2 minus 2 times row 1. 2, -1, -2, 0. We'll take negative row 2 now and make that 0, 1, 2, 0. And then row 1 minus row 2, and then we will have reduced echelon form. 1, 0, 1, 0, 0, 1, 2, 0. So this tells me that x is plus z is equal to 0, and y plus 2z is equal to 0, which means that x is -t, y is -2t, and z is t. And so x, y, z is t times the vector -1, -2, 1. And so the null space of A is the span of the vector -1, -2, 1. And we have an answer. So we solved the homogeneous system and then write the solution set as if in the form of a span. All right. So definition, say we have any subspace. If the vectors that we are using in the span is also a linearly independent set, then we say that we have a basis for the subset. So last time we talked about having a basis for Rn. Now we can have a basis for just a subspace inside Rn. It is a spanning set that's linearly independent. Linearly independent means it will have a leading entry in every column. But if it's only basis for a subset of Rn and not all of Rn, then it won't have a pivot in every row because it will only span part of Rn. So we still have a pivot in every column. May not have a pivot in every row. Or to be clear, I'll say may or may not have a pivot in every row. Either is possible. And if we have a set with n vectors, then we say that the set of space has n dimensions. We've used the word dimension informally. We sort of know that 2 dimensions is a plane and 3 dimensions is a solid. We now have a fancy definition for dimension that we can calculate. So it's the number of base vectors in a basis. All right. So let me issue a word of caution here. There's a difference between a basis and a subspace. A basis is just the vectors that we use to build the subspace. This has just n vectors in it. The subspace is not just an original set of vectors, but it's all of the linear combinations. This has an infinite number of vectors. All linear combinations are included. So subspace is much, 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 much larger than its basis. So in 3 dimensions, my basis is only going to have 3 vectors in it, but my span is going to have an infinite number of vectors. And so don't get these confused. I've seen people in the past on exams that aren't sure when to write the word span or not. A basis never includes the word span, and a subspace always does. Okay? Let's move on. We could always start with a basis and form a subspace by taking the span of B. That is, let me go back to the previous slide here. That is, if I have a basis and I want to go to the subspace, literally all I have to do is just put the word span out in front of it. But I can't go the other way around. If I have a subspace and I want to find the basis, I can't just take off the word span and be done. Because, I'm going to go back one more slide, the basis has to be linearly independent, which means we can only have the columns with pivots in them. There has to be a pivot in every column. And so if the set is not linearly independent, then we could have a subspace that's a span, but then when we take off the word span, it's not yet a basis. That can happen. So I can always go from basis to span by basis to subspace by adding the word span. I can't go automatically from span to basis by just taking away the word span. I also have to check for linear independence. We'll do a couple of examples. Let me show you how this works. So let's say we have a set of vectors that forms a basis for Rn. It will have a pivot in every row, but a set of vectors that forms a subspace for Rn might not have a pivot in every row. We mentioned that a moment ago. So it can have a pivot in every row, but it might not, depending on whether we are spanning the entirety of Rn or just a subspace of Rn. If we have a subspace, but the set is not a basis, then there is some subset that's a basis. So that is, I can find a basis by getting rid of the vectors that don't have pivot positions in them. And here I think we're finally ready to do an example. Let's find a basis for this set. Now I can tell just by looking that I can't have a pivot in every column because I have 4 columns and only 3 rows. So this is not linearly independent. So let's go ahead and reduce this. 1, 0, 2, 0, 2, 4, 1, 4, 10, 0, 3, 7. I'm going to take row 3 minus 2 times row 1. Two minus 2 is 0. 4 minus 0 is still 4. 10 minus 2 is 8. 7 minus 0 is 7. All right, so now I have a leading entry here, and I want to get rid of the 4. So I'll do row 3 minus row 2 times 2. So that gives me 1, 0, 1, 0, 0, 2, 4, 3. 4 minus 4 is 0. 8 minus 8 is 0. 7 minus 6 is 1. And now we find that column 3 has no pivot in it. And that means that the basis is the set 1, 0, 2, 0, 2, 4, skip the column 1, 4, 10, and keep the column 0, 3, 7. That is, we don't need this column to form the basis. It has no leading entry in it. Okay? All right, let's try these. Do these vectors form a basis for R3? So to be a basis, we need a linearly independent columns. So we will check to see if that's true. 3, 0, negative 6, negative 4, 1, 7, negative 2, 1, 5. I'm going to take row 3 plus 2 times row 1 to get rid of that negative 6. Let's see. 7 plus negative 8 is negative 1. 5 plus negative 4 is positive 1. And so then if we take row 3 plus row 2, we get 3, negative 4, negative 2, 0, 1, 1, 0, 0, 2. And we do have leading entries in every column, and so the answer is yes. We do have a basis. All right. So we're going to quickly go back and look at column space, row space, and null space, and talk about how to find a basis for these. To find a basis for the column space, we're going to row reduce that matrix to identify the columns that contain leading entries. The basis is going to be the set of just the vectors found in the columns of the original matrix. And that will be a basis for the column space of A. So let's do an example. Find a basis for the column space of this matrix. This matrix is already in echelon form. You're welcome. And my leading entries are in these 3 columns. And so the basis is the first column, the third column, and the 5th column. All right. Let's try another example. Let's find a basis for this matrix. Oh, this matrix is not an echelon form, but when we put an echelon form, the matrix we get is A from the previous example. Is this matrix right here that has leading entries in columns 1 and 3. 1, 3, and 5, sorry. So I want to keep columns 1, 3, and 5. And so my basis is 1, 3, 2, 5, skip column 2, 0, 1, 1, 2, skip column 4, and negative 1, 5, 2, 8. And that gives me a basis for column space of B. All right. We reduce, we find the echelon form. Whichever columns have leading entries, we then go back to the original matrix to pull the numbers. So the numbers of the vectors come from the original form of the matrix. All right, let's keep going. How do we find a basis for a null space? We don't need a special procedure to find a basis for the null space. The procedure that we covered in the previous examples always automatically produces a basis. We'll do an example anyway, but we don't need to learn anything new. So if I have this vector set here and we want to find a basis, we augment with zeros. And we row reduce. So when we do row 3 plus row 1, that gets rid of that bottom row. I'll take row 2 divided by 2 to get a 1 for the leading entry. And then we'll take row 1 minus row 2. And we have that x plus z is equal to 0. Y plus 2z is equal to 0, which means that x is equal to negative t, y is equal to negative 2t, and z is equal to t, which is the same thing as saying that x, y, z is t times negative 1, negative 2, positive 1. Or, to answer to the point here, the basis for the column space of A, and since it's a basis, I don't put the word span here. It's just a set negative 1, negative 2, positive 1. And that gets me the basis. All right. Oh, bear with me. We're almost done. Definition here, rank and nullity. We've seen the definition rank before. The rank of a matrix is the number of leading entries in an echelon form. The nullity is the number of columns that don't have leading entries. The nullity is the dimension of the null space of A. So if I have a 3 by 5 matrix, let's say A is a 3 by 5 matrix. The echelon form of A looks like this: 1, 0, 0, 0, 1, 0, 0, 1, 0, 3, 5, 0, 0, 0, 1, and negative 2, 3, 2, where my leading entries are here. The rank is 3 because there are 3 leading entries. The nullity is 2 because there are 2 columns that don't have a leading entry, or two free variables, if you want to think about that. And that means that the dimension of the column space of A is 3, but the dimension of the null space of A is 2. The rank theorem is a really obvious theorem once you understand what it's saying. If A is an m by n matrix, n is the number of columns, then the rank and the nullity have to add up to n when we add them together. Let's go back to that last example. I have a 3 by 5 matrix. 3 of the columns have leading entries, 2 of the columns don't. When I add these two numbers together, all 5 columns are represented. And so the rank and the nullity always add up to n. What we can do with this theorem, though, is we can use it to answer theoretical questions without having to do some row reduction. For example, can a 6 by 9 matrix have a two-dimensional null space? Is that possible? So a 6 by 9 matrix has 6 rows, 1, 2, 3, 4, 5, 6, and 9 columns, 4, 5, 6. By the time I finish writing all this out, you'll probably have figured out what the answer is. Well, to have a two-dimensional null space, we would have to have a nullity of 2, which means we would have 2 free columns, which means all the other columns would have to have leading entries in them, but we only have 6 places where pivots could go because there are only 6 rows, which means we have to have at least 3 free variables. And so the answer to this question is no, it can't happen. Because the maximum rank is 6, and so the nullity has to be at least 3. We cannot have a two-dimensional null space. I don't have to do any more work than that to answer this question. I can answer this as a theoretical question without having to do a lot of computations. Let's try another one. What is the largest possible rank of a 4 by 7 matrix? Well, the rank is the number of leading entries, the number of pivots. Since I only have 4 rows, that's the most pivots I can have. So I can't have a rank that's larger than 4, which means I can't have a column space that's more than 4-dimensional. If a matrix has 0 nullity, what is its rank? That means out of these n columns, none of them are free, so the rank has to include all n columns. The rank has to be n. I have a 5 by 7 matrix that has a two-dimensional null space. That means 2 of the columns are free, which means all the other columns have to have pivots, which means I have to have 5 pivots. So we must have a rank of 5. And the question then says, do the columns span R5? Well, to span R5, we need a leading entry in every row. Leading entry, spanning means we have a pivot in every row. Spanning R5 means we have a pivot in every row. Linear independence means we have a leading entry in every column. In this case, we have to have a leading entry in every row because only 2 of the 7 columns are free. And so the answer to this question is yes. All right. That wraps things up for today. I know this was a long video. Thanks for bearing with me. Y'all have a great day. You take care.